Hi everyone. This is the conclusion and summary lecture for the course optimization techniques. Let me share the screen. Okay. So, as I said, this is the conclusion and summary lecture for the course. If you haven't seen the bonus lecture on Riemannian optimization before this lecture, please take a look at that. First off, some additional notes that we had we couldn't cover in this course, but they are worth looking at. So the first one is the family of methods named cut-in plane methods. And what is that? So cut-in plane methods, also called localization methods, are a family of methods which start with a large feasible set containing the solution to be found. So we have a large feasibility set. Do you remember what was the feasibility set? The set of constraints determined by equality and inequality constraints. So we start with that, and it is determined by inequality constraints, equality constraints, and the domain of the optimization variable. We start with that. Then iteratively, we reduce the feasibility set by cutting off some piece of it. So an example is this, shown in this figure. Credit of image is for reference 1. So we have a feasibility set. In this case, it's just a polyhedron. And then we divide this feasibility set to 2 pieces. So as it is 2D, only a line is required for division. But in higher dimensions, we need hyperplanes or some other higher dimensional boundaries. So we divide the feasibility set to 2 parts, like here, first part and second part. And then we, with some algorithms, we decide or guess where the solution should be. So if we know that, for example, the solution must lie in part 1, then we get rid of the other part, and then our feasibility set reduces to be only part 1. So this is, in this way, at every iteration we are making the feasibility set smaller and smaller in cut-in plane methods. So for example, a cut-in plane method starts with a polyhedron feasibility set. An example, it might not be necessary, it doesn't need to be a polyhedron feasibility set. Then it finds a plane or hyperplane at every iteration which divides the feasibility set into 2 disjoint parts, one of which contains the ultimate solution, the solution that we want to find. It gets rid of the part without the solution, so we throw away the part which won't have the solution, and this reduces the volume of polyhedron or the volume of the feasibility set. This is repeated iteratively until the polyhedron feasibility set becomes very small, and converges to the solution. So it becomes smaller and smaller until it becomes very small and goes almost to the ultimate solution that we want to find. One might be wondering how it's like a chicken and egg problem. Why? Because if we already knew where the ultimate solution is, then the problem would be solved. So why do we need to make the feasibility set smaller and smaller to reach to that ultimate solution? The thing is that when we are dividing the feasibility set into 2 parts every time, we don't know where the ultimate solution is, but we can guess which part of the feasibility set it lies in. So using some algorithms, which I'm not gonna mention their details here, the cut-in plane methods know that the ultimate solution must lie, for example, in part 1 or in part 2 in this division, in the feasibilities of the feasibility set. But we don't know where it is. If we knew where it is exactly, then the problem would be solved, and we didn't need to start with the feasibility set and converge to that. If we already knew the solution, that would be done. However, we can know which part it lies in. It must lie in, so we can get rid of the other one, the other part. That's the philosophy and idea behind the cut-in plane methods. And this is somewhat generalization of the bisection method. Bisection method, also called binary search method. It is a root finding method. So when we want to find the root of a function, we can have binary search, and you might have learned it in your numerical analysis courses. But later it was used for the binary search, or bisection method was used for convex optimization. So the bisection method, what does it do? It halves the feasibility set, halves it, and removes the part without the solution at every iteration. Okay. Binary search method, what does it do? It halves the feasibility set into two exactly equal parts, and then removes the part without the solution. An example of bisection method or binary search method is the game that many of us have done. So I say I have a number between 1 and 1,000, for example, or 0 and 1,000 in my an integer number in my head, and then you guess it. The fastest way to guess this number in my head is that you do the binary search algorithm. And after every guess that you give me, I can say that the number in my head is whether above this number or above the number that you suggested, or below that. So if you want to converge to the number in my head in the fastest way is to use a bisection method. Some people don't use the binary search or bisection method, and they might not reach to the number in my head, or it may take a long time for them to guess my number. So binary search is the fastest for that. For example, you might say, so what is the middle number between 0 and 1,000? Is 500. 500. Then you say whether it's 500, and I say, okay, no, it's above that. So you remove the whole range between 0 and 500. Then your range becomes between 500 and 1,000. Then you say, what is the number between 500 and 1,000? Exactly in the middle of it. It's 750, right? And then you say whether it's 750. For example, I say it's below that. So you remove the whole range between 750 and 1,000, and your range becomes between 500 and 750. Then you halve it again. So in this way, you will converge to the number that I have in my mind. So that's the idea behind my binary search algorithm. So you can use that for root finding methods. So that your root, so you can start with a big domain, and your root, the root of the function, lies in this domain. And then you make this domain smaller and smaller until it converges to the root of the function. You can use the same method for optimization, where you have some minimum or maximum of a function, and you start with a big feasibility set, and then you halve it at every time until the feasibility set becomes smaller and smaller and converges to your solution. And this is an example of this binary search algorithm for optimization. So we start with some lower bound and upper bound, L and U. Iteratively, at each iteration, we find the middle point between lower bound and upper bound. So we halve it. At every iteration, we found the middle point, and we check whether at that point, so whether at that point our gradient is negative or not. If it is negative, then we set the lower bound to be x. So L was here, U was here, okay? We halve it. So this is the middle. So this equals this. This is for a scalar case, but you can generalize it to have it for multi-dimensional case. Then in this case, you'll say whether the gradient at this point is negative or not. If yes, then you need to get rid of this and set L to be this. Right? So your feasibility set becomes only this part, which is smaller. Otherwise, you will set this to be, you will get rid of this part, and your feasibility set becomes only this. So this was the previous L, and your new U upper bound is the xk plus 1. And the new feasibility set is this. So you halve it at every time until you converge, and you can check the convergence criterion. When is it, for example, one convergence criterion might be the number of iterations, the other one might be whether the gradient becomes almost zero or not because of the first order optimality condition, or whatever what I said at the, because we know that at the solution, ultimate solution, the gradient must be zero, right? And if it is converged, that then you return x the middle point that you have found, because it becomes a small, too small, that L and U become very close to each other, so their middle point is almost the solution. Some of the important cut-in plane methods are center of gravity method. So these are some algorithms for in the cut-in plane, in the family of cut-in plane methods. Center of gravity method, maximum volume ellipsoid, MVE, cut-in plane method, Chebyshev center cut-in plane method, analytic center cut-in plane method, or ACCPM. You can take a look at references 3 and 4 and 5. So what the difference between these is how you divide the feasibility set. So note that in bisection method is a special case of cut-in plane method, because you know that your division point of the feasibility set is exactly the middle of the feasibility set, because you are halving the feasibility set. However, in cut-in plane methods in general, there are different ways to cut your feasibility set into two parts, and the two parts don't need to be equal size. So how can we define the cut-in plane or the cut-in point in the feasibility set? Then there are different algorithms to do that. One way is to choose the center of gravity. The other one is maybe maximum volume ellipsoid. The other one is the Chebyshev center of the feasibility set, or analytic center. So you have different ways to find the center, and then from that center you divide the feasibility set into two parts. Similar to subgradient methods, cut-in plane methods can be used for optimizing non-smooth functions. So you can use the cut-in plane methods for the sake of non-smooth optimization as well. Okay, now another thing which we haven't covered in this course and is worth looking at is ellipsoid method. Ellipsoid method, it was developed by several people. We can take a look at references 6 and 7. It was proposed in 1976 and 1977 by the papers 8, 9, 10, and 11. It was initially applied to linear programming in a famous paper in 1979, reference 12. It is similar to cut-in plane methods in cutting some part of the feasibility set iteratively. So it is in this sense, in the sense of cutting some part of the feasibility set iteratively, it's very similar to the cut-in plane methods. What does it do? It at every iteration, it finds an ellipsoid centered at the current solution. So when you have a current solution, xk, we have an ellipsoid denoted by E centered at xk, and P is just the you can take, it's a parameter of the ellipsoid, which is the matrix here in the middle of this equation. So this defines the interior of an ellipsoid, and this P needs to be symmetric, positive, definite. And we have P inverse here, and this is the set Z for all Z minus xk transpose P inverse Z minus xk. So this is a quadratic form. It should be less than or equal to 1. This is the equation for the interior of the ellipsoid, because it has less than or equal to. So interior and the boundary of the ellipsoid centered at the point xk. That's why you say it's centered at the current solution. So this is the ellipsoid. At every iteration, it finds this ellipsoid. You can see an example in this figure. Credit of this image is reference 13. So we have the current solution xk, and this is the ellipsoid. Current solution xk, the ellipsoid epsilon k, centered at xk. This is the ellipsoid, and this is this can be the ellipsoid of the next iteration. So what does it do? As you see, it removes half of the ellipsoid which does not contain the solution. So similar to the idea of cut-in-plane methods, it's saying that let's take the ellipsoid centered at the current solution and then get rid of half of the ellipsoid which doesn't have the solution. How is it different from the cut-in-plane methods? Cut-in-plane methods, it uses a hyperplane. That's for cutting the feasibility set. That's why we call them cut-in-plane methods. However, what ellipsoid method does is that it just finds an ellipsoid centered at the current solution, halves it like this, exactly like this, that it has halved these ellipsoid, and then it says that it finds out where the solution lies in, and then it removes the other half. By the way, in both cut-in-plane methods and ellipsoid methods, we can use the direction of gradient for guessing whether the solution is in which part. Because assuming that this is a convex solution, convex optimization problem, then if in the direction of gradient, we know that we are getting away from the solution. So minus direction of gradient should be the direction of this solution. That's why when we have that feasibility set, then we can find out which side of the feasibility set, or here in this case the ellipsoid, we should move toward, and which half which half of that we should get rid of. Again, another ellipsoid is found at the updated solution, so we do it iteratively. This is repeated until the ellipsoid of the iteration is very small, so the ellipsoid becomes smaller and smaller, right? And it converges to the solution. So this is the idea of ellipsoid methods in optimization. Another thing which is worth looking at, which we didn't go through much, is the minimax and maximin problems. Consider a function of two variables, x1 and x2, f of x1 and x2, and the following optimization problem. Minimize with respect to x1, maximize with respect to x2, and the objective function is f of x1 and x2. So first we maximize with respect to x2, and then we minimize with respect to x1. In this problem, we want to minimize with respect to one of the variables and maximize with respect to other variable. This optimization problem is called minimax problem. Why? Because we are saying the minimize, maximize f, minimum of maximum of f, right? So minimax, minimum, maximum, minimax of f. If we have the other order, so we first minimize with respect to, maximize with respect to x1, and then minimize with respect to x2. Compare these two equations. This one was minimized with respect to x1, maximized with respect to x2. This one is maximized with respect to x1, minimized with respect to x2. Yeah. And this is called maximin problem. Why? Because first we have maximum or maximize, then minimize. So maximum, minimum, maximin. The other one was minimax, and this is maximin problem. And under certain conditions, the minimax and maximin problems are equivalent if the variables of maximization or minimization stay the same. So here, for example, maximization is with respect to x2. Like here, let's consider this case. Maximization is with respect to x2. Again, here maximization is with respect to x2. Minimization here is with respect to x1. Here also, minimization is with respect to x1. So what does it mean? It means that we have simply changed the order of these two. If we do that, under certain conditions mentioned in reference 14, which is a book, these two are equivalent. Note that if you change this x2 to x1 and this x1 to x2, then they are not equivalent under any conditions. They are equivalent under some conditions if the variables stay the same. For the variable of maximization is x2 here, here is also x2. The variable of minimization is x1, here is also x1. All right, okay. I think it's intuitively also understandable. So the only thing which has changed between these two is the order of maximization and minimization, and under some conditions they are equivalent. So this, the left-hand side in this is saying that first maximize the function with respect to x2 and then minimize it with respect to x1. The right-hand side, on the other hand, says first minimize the function with respect to x1 and then maximize it with respect to x2. Okay. In the minimax and maximin problems, the two variables have conflicting or contrastive desires. One of them wants to maximize a function, while the other one wants to minimize it. So they have conflicting desires, right? Hence, they are widely used in the field of game theory as important strategies. You can take a look at reference 15. Why? In game theory, you usually have some agents which are either competing with each other, or sometimes they want to collaborate with each other. And in the case where the agents want to compete with each other, we can use minimax or maximin. Why? Because one of them, for example, here in the left-hand side, assume this is the payoff of something. The agent 2x2 wants to maximize this payoff. However, agent 1 wants to minimize this payoff. Consider as an example, this payoff might be the payoff of only x2. So it's good for x2, but bad for x1. Therefore, x2 wants to maximize it. x1 wants to minimize it because x1 is the enemy of x2 or a competitor of x2. So in game, that's why it has a lot of use cases in game theory. Some examples of game theory is, for example, in machine learning generative adversarial networks, GANs, where we have a generator which wants to generate some fake data, and we have some classifier which wants to distinguish the fake data from the original data. Okay, and the generator wants to fool the discriminator or the classifier such that it generates very good and realistic data, that it fools the classifier or the discriminator, and the discriminator can't find out whether that's a fake generated data or an original data. And in this way, for example, assume F here is the cross entropy or some classification loss function for the discriminator to discriminate the fake generated data and the original data. So we know that the discriminator, assume it's x1, wants to minimize this loss function. However, the generator wants to maximize this loss function because it's the enemy of the discriminator. In this way, that this is an example in machine learning. Another example is in economy, where minimax and maximin are used a lot, because when you have a duopoly in finance and in economy, so there are two, for example, two or multiple agents which are competing with each other. So an example is, I don't know, such as Google and Microsoft. So they want to compete with each other. One of them wants to maximize its payoff, the other one wants to minimize that payoff, something like that. So they are competing with each other, especially in duopoly. In economy, you can see that. Okay, now let's have a summary. So the additional notes is over. And now let's have a summary of what we have learned in this course. The course provided the main methods of optimization. First off, yes, okay. We started with preliminaries, including sets, norms, functions, local and global minimizer, derivatives, gradient, Jacobian, Hessian, convexity of sets, and convexity of functions. We covered these things in preliminaries, right? We also introduced the standard problems such as convex problem, optimization problem, linear programming, quadratic programming, semi-definite programming, and these forms in the preliminaries as well. We covered linear programming. We introduced this simplex algorithm and its tableau method implementation for solving the linear programming problem. Also, we introduced integer linear programming, which is linear programming where the variables or some of the variables are discrete and integer. We also covered the branch and bound method for integer linear programming. We introduced Kerouac-Cohn-Tucker or KKT conditions. We also covered Lagrangian function and the method of Lagrange multipliers. Do you remember? We also covered unconstrained and constrained first-order optimization. So for unconstrained first-order optimization, we covered gradient descent, backpropagation, accelerated gradient method or AGM, stochastic gradient descent, SGD, SAG, Adam, neural network, and these things. We also covered proximal methods in order to tackle constraint first-order optimization, such as projected gradient method. We also covered unconstrained and constrained second-order optimization. In second-order optimization, we need both first-order and second-order derivatives. We covered Newton's method for unconstrained second-order optimization. We also covered interior point method, also called barrier methods, such as log barrier method for constrained second-order optimization. And we also covered decomposition methods and conjugate gradient methods for accelerating Newton's method for second-order optimization. We also introduced quasi-Newton's methods such as BFGS and limited memory BFGS, LBFGS for approximating the Hessian or inverse of Hessian in Newton's method. We also went through distributed optimization, such as alternating optimization, as well as ADMM or alternating direction method of multipliers in order to solve complex multivariate optimization problems. Right, okay. We covered non-smooth optimization. And we covered all of these for non-smooth optimization. Approximation by convex conjugate and Huber function. So we said that let's approximate the non-smooth parts of the function by some smooth functions, such as Huber function. For Huber function, we introduced convex conjugate to define Huber function. We also covered proximal algorithm, self-thresholding, coordinate descent, and subgradients. We also covered non-convex optimization, including, so we divided non-convex optimization methods into local methods and global methods. Local methods are faster, but they don't guarantee the global solution. Global methods are slower, but they can guarantee and verify the global solution. So for local optimization methods, we covered sequential convex programming, which also had a trust region in it. For global optimization method, we covered branch and bound method, which has a tree structure method. We covered important search-based or metaheuristic optimization methods for handling highly nonlinear and highly non-convex optimization methods problems. And among those, we covered some of them, such as genetic algorithm, particle swarm optimization or PSO, simulated annealing, and also we covered null-der-Meet simplex algorithm, which is used in fmin search of MATLAB. Finally, we introduced Riemannian optimization for optimization on Riemannian matrix manifolds, and that was a bonus lecture in this course. We also, in this session, we briefly went through cut-in plane methods and ellipsoid method and Minimax and maximin problems, right? Okay, now let's talk about dealing with an optimization problem. Now that we have learned all of these, when we have an optimization problem, how can we deal with it? How can we solve it? Assume we have an optimization problem where we want to minimize or maximize a cost function, and we might have several equality and or inequality constraints. So first off, we are minimizing or maximizing some function called cost function or objective function, and we might or might not have constraints. If it is, we don't have constraints, it is an unconstrained problem. If we have constraints, it is a constraint problem. Among the constraints, we might have equality constraints and or inequality constraints, right? So we have several cases. First off, it might be minimization or maximization. Also, in each of these, we might not have constraints, or we might have constraints. If we have constraints, we might have only equality constraints. We might have only inequality constraints. We might have a mixture of both equality and inequality constraints. Okay, so all of these cases might happen. If the problem is on constraints such as this, minimization, minimize f of x with respect to x, then what do we do? The first thing which you should do in optimization, take derivative and set it to 0. Why? This is because of first order optimality condition. It says gradient of f at the solution minimizer x star needs to be 0 or needs to vanish to 0. This is also, you can see it as one of the, as a consequence of one of the KKT conditions. And this is high school rule. Do you remember in the course, whenever I refer to this first order optimality condition, I said, what did we do in high school? We take derivative and set it to 0. Because in high school, we also want, whenever we wanted to find an extremum of the function, a minimum or maximum of the function, what did we do? We used to take derivative and set it to 0 because we know the gradient is 0 at these points. Okay, so take derivative, set it to 0. If you can find x star in a closed form solution. What do I mean by closed form? It means that the left hand side, for example, is x, and the right hand side is an expression, a mathematical expression without x in it. So you could find x alone in a closed form solution. Then that's done. You might have a set of x stars, some, because you might have some minimums and maximums. Like if it's not convex, we might have, for example, here 3 minimums and 1 maximum. So if it's convex, then we know we only, if it's strongly convex, we only have 1 minimum. If it's convex, we might have several minimums, but all of the function value in all of those must be the same if it is convex. Okay, so x star gives, if we can find it in closed form solution, then we need to check whether it's a minimum or maximum or a saddle point. Why? Because this is maximum, this is minimum, this is a saddle point. In all of these, the gradient is 0. How do we know which one it is? Because we might find several x stars. One of them might be minimum, one of them might be maximum, one of them might be saddle point. So we can take second derivative, calculate it, and at that point, x star, we should check second derivative of at that point. If it is positive semi-definite, or in a scalar case, it is positive, greater than or equal to 0, for all of x's in the neighborhood at that point. So what do I mean? I mean, at that point and all of the points near that point in the neighborhood with some radius epsilon, right? If we know that this second derivative is greater than or equal to 0, or in the, if we are we have multiple dimensions, then it needs to be positive semi-definite. If that's the case, it means that we are in this neighborhood, and as its second derivative is greater than or equal to 0, the function is facing up. Therefore, this must be a minimum. If the second derivative is less than or equal to 0, or is negative semi-definite, in this case, it's the function at the neighborhood around that point is facing down. So it must be a maximum, a local maximum. If at some points in this neighborhood, the function is facing down, and at some points it's facing up. For example, in this case, in this neighborhood is facing down, it's in this neighborhood is facing up. So in this neighborhood, at some points it's facing down, at some points it's facing up. Then that point is a saddle point. That's why I said for all points in this neighborhood, if it's greater than or equal to 0, it means that it's facing up for all points in this neighborhood and it's a minimum. Okay. If we can't find a closed form solution like this, then we need to do numerical optimization. Why? It's the same as root finding. When you want to find the root of something, what do? You set it to 0. You set the function to 0. Hopefully you can find it in a closed form solution. If you can't find x in a closed form solution, the root, then you need to use numerical analysis. What have you learned in your numerical analysis course? You do it iteratively until you find. And there is a close connection between root finding algorithms and optimization. Why? Because in root finding algorithms, you want to find the root of f of x equals 0, right? And in in optimization, you want to find the root of gradient of f of x equals 0, because of the first order optimality condition. So if you replace the function f with the gradient of f, then the optimization problem is just a root finding problem, right? Therefore, if you can find the solution in a closed form solution, done. You need to also check this to check whether it's minimum, maximum, or saddle point. If you can't find a closed form solution, then you need numerical analysis, as you have done in your numerical analysis for root finding algorithms. So you need to do it numerically or iteratively. Then it divides into two family of methods, whether first order optimization or second order optimization. In first order optimization, you do it iteratively in numerical optimization, but it needs only first order derivative, gradient of f, or gradient. If you have second order optimization, you need both first order and second order. And first order derivative is called gradient usually, and second order derivative is called Hessian usually, right? So now you see the connection between root finding algorithms and numerical optimization, right? Why do we call it numerical optimization? Because it's using numerical analysis and it is iterative. Okay. If the problem is constrained, such as this, minimize a function f of x with respect to x subject to m1 inequality constraints and m2 equality constraints, and each of these are functions of the variable x. Then we can do several things. One thing is that we can convert the constraint optimization problem to an unconstrained optimization problem. How? We can embed the constraint into the objective function using penalty or regularization term. Then we have two cases in this case, whether we can have soft penalty or hard penalty. For soft penalty, we can say, okay, put each of these inequality and equality constraints as penalty terms or regularization terms for penalizing deviation from these constraints. And you can also have some weights, like here, to weight how important the deviation is with respect to the function itself. So here we have lambda i's, we have nu i's here. It's similar to the form of Lagrangian of these functions, because Lagrangian is kind of, you can interpret it using soft penalty too, right? Then you are minimizing it, and these are the regularization terms. Here we have m1 inequality constraints and m2 equality constraints. Why? Because here you want to minimize hi2 to become 0. Here we also want to minimize yi2 to become less than or equal to 0, right? So you can see these terms as some penalty term for x belonging to the feasibility set S. And this feasibility set, you can see it as an intersection of all of these constraints. And I have put the weight or regularization term eta for it. Doesn't matter. And I have defined this soft penalty in this case. If it is satisfied, so if all of these constraints are satisfied, x belongs to the feasibility set, then it's 0. So penalty is 0. If it's not satisfied, then this function needs to be an increasing function with respect to not being in the feasibility set. So the more we are deviated from the feasibility set or the set of constraints, the more this function should get. The more the output of this function should be. The more we have deviation, the more penalty we have. Okay. However, we can have hard penalty. Then the penalty term needs to be a hard penalty term. So it needs to be an indicator function. An indicator function in optimization usually is defined as this. So if X belongs to the feasibility set, so it satisfies all of the constraints, then this indicator gives 0, similar to the penalty, soft penalty. However, the difference is for not being in the set, feasibility set. If it's not in the feasibility set, the hard penalty or indicator function in this case says it should blow up to infinity. So it blows up the whole regularized objective function, because this is a regularized objective function. This is the objective function. This is the regularized objective function. Also, here in soft penalty also, this is objective function. This is regularized objective function. It is regularized by the penalty term. However, in the hard penalty case, the regularization term is an indicator function, which is hard. It blows up the regularized objective function to infinity, which kills the optimization problem for minimization. Because minimization, infinity is exactly the opposite of minimization. If you are maximizing it, then that should become negative, minus infinity, because that would kill maximization, right? So we also can have approximation of hard penalty, because this is not easily implementable in, we can't implement it easily in computer. Therefore, we need to approximate it, because it's like this, function like this. Then what should we do? We need to approximate it with some function like this, and that can be implemented by logarithm or other functions. Then those are barrier methods, because it's like a barrier, but we are approximating it with some function which can be implemented in computer. And one of the barrier methods is log barrier or logarithm barrier method, because it can approximate this indicator function by logarithm. And these barrier methods are used in interior point methods for second order optimization and widely used in optimization toolboxes, right? Okay. If the problem is linear programming, affine costs or constraints, then we can solve it using the simplex algorithm. Any of its implementations, such as tableau method. So when the cost function is affine or linear with bias is kind of affine function. Also, if the constraints are affine functions, so the feasibility set is just a polyhedron, then we can use linear programming. And for that, we can use simplex algorithm. Linear programming can be solved by other algorithms, such as interior point method too. Simplex algorithm is the simplest one. If the problem is integer linear programming, so affine cost and constraints, but some or all of the variables are integer, then we need to use branch and bound method. And in each the sub-problem in the tree of the branch and bound method, we can use simplex algorithms such as the tableau method for solving that. Right. By the way, if the linear programming has 2 or 3 variables only, then we can use the visualization for solving the optimization problem. Okay. In general, if the optimization problem, not just in linear programming, has only 2 or 3 variables, maybe we can solve it by visualization. Visualization is the easiest way to solve an optimization problem with 2 or 3 variables, right? Okay. If the optimization problem is not linear, but not very complicated, we can solve it using method of Lagrange multipliers, which makes use of KKT conditions. Do you remember? We solved an example in the KKT slides, and that was not a very complicated problem. Why? Because when it becomes very complicated, then the KKT conditions become very complicated, and the system of equations becomes very complicated to solve. If it's complicated, solving the system of equations in the method of Lagrange multipliers is very hard. If the optimization problem is unconstrained, then we can, and it doesn't have a closed form solution, we can use either first order optimization methods or second order. First order methods, unconstrained first order methods, they are slower, but they are easier compared to second order methods, which are faster but harder. Why? First order method that only needs gradient, so it's easier, but it's slower. Its convergence rate is slower than second order method. Second order methods, they are faster, their convergence rate is much faster, but they are harder. Why? Because they need to calculate both gradient and Hessian, and calculation of Hessian is hard. That's why they usually approximate the calculation of Hessian by quasi-Newton's methods and these things. Also note that the convergence rate of first order methods was slower. That's why they tried to accelerate those methods, such as accelerated gradient method proposed by Yuri Nesterov. Do you remember? But again, still, Newton's method is faster to converge. And that's why in many machine learning algorithms, nowadays, they are using first order method. Why? Such as in backpropagation and neural networks, because they don't want to calculate the Hessian and second order derivatives. A pain in the neck. It's a headache. So first order optimization, such as gradient descent, backpropagation, accelerated gradient method, stochastic gradient descent, SAG, ADAM, neural network, unconstrained proximal methods, right? Second order unconstrained methods such as Newton's method. However, if the optimization problem is constrained and we don't want to convert it to an unconstrained problem using embedding as soft or hard penalties, which we discussed here. If we don't want to do that, we want to actually solve them using the feasibility set and constraints, then we can use constrained first order and second order optimization methods. Constrained. Okay. So again, first order methods are slower but easier, and second order methods are faster but harder. Some constrained first order methods, which do it iteratively, are projected gradient method and constrained proximal methods. Right. For constrained second order optimization, we can use interior point method, log barrier method, and these things which are used in toolboxes, right? Such as CVX. We can also use decomposition methods, conjugate gradient, and quasi-Newton's method to make second order optimization easier and faster, right? Okay. If the optimization problem is distributed or with multiple variables, then we can use distributed optimization, such as alternating optimization and ADMM, or alternating direction method of multipliers. And also we can make it parallel. Why? Because it's a distributed algorithm. So we can parallelize it on different servers. It's closer related to also federated learning and machine learning. You remember? If the cost in the optimization problem is non-smooth or non-differentiable at least at one of the points in its domain or feasibility set, then we can use non-smooth optimization. For example, we can approximate it by convex conjugate and Huber functions. So we can approximate the non-smooth parts of the function by a smooth function, such as Huber function. We can use proximal algorithm, soft thresholding, coordinate descent, and subgradients. If the optimization problem is non-convex, the cost is, so what do we mean by non-convex optimization problem? Recall preliminaries. If the cost is non-convex and or if a cost is not a convex function and or the feasibility set or the constraints are non-convex sets, then we can use non-convex optimization. So we can have two approaches. Local optimization methods, which are faster to converge, but they don't guarantee to find the global solution. such as sequential convex programming, which at each iteration, it approximates the optimization problem to a convex optimization problem. So it convexifies the problem, or it relaxes the non-convex optimization problem to a convex optimization problem. But it has a trust region to make sure that we don't deviate from the actual solution much. We can use global methods, which are slower to converge, but they guarantee to find the global solution, and they can verify it also, such as branch and bound method using the tree-based algorithm. We can also use non-convex optimization or search-based optimization, metaheuristic optimization in these cases. So if the optimization problem is complicated or highly non-convex, we can either use non-convex optimization or metaheuristic, also called search-based optimization, right? If it's highly non-convex or highly nonlinear. Also, if in these two cases, we have to use metaheuristic optimization too. If the gradient of the function is hard to compute, because we know that the classic optimization algorithms, they need to use gradient. Why? Even from starting point, we take derivative and set it to 0, we need gradient. If not closed form solution, we need to do it iteratively by first order or second order optimization, both of which require gradients, right? Therefore, we need to have gradients. If the gradient is hard to compute, then we can use metaheuristic, because search-based methods usually don't use gradients, right? Or when the function is not known, but it works like a black box. So we have f. Whenever we give some input, it gives us f of x. In this case, it gives us an output for each input, but we don't know inside of it. It's exactly similar to a black box, and it's used in reverse engineering too, because in reverse engineering, we don't know inside the function, but we can always test it with some point, and it gives us some output, right? So when it's like this, then we have no choice but to use metaheuristic optimization or search-based. Why? Because in this case, we can evaluate the function, but we don't know what it is. And metaheuristic optimization methods or search-based optimization methods, they usually evaluate the function at some solution. So we have some candidate solutions, and we evaluate the objective function or the fitness function or whatever we call it at those candidate solutions and their local searches too. So we only evaluate the function value. So in these cases, we have to use search-based optimization. Some examples of metaheuristic or search-based optimization are genetic algorithm, particle swarm optimization, or PSO, simulated annealing, Nelder-Mead simplex algorithm used in FBIN search of MATLAB and DC. If the feasibility set or set of constraints can be seen as a Riemannian manifold, then we can use Riemannian optimization. Take a look at our bonus lecture on Riemannian optimization. An example is that minimize trace of X transpose AX with respect to matrix X subject to X transpose X equals identity matrix I. This is used a lot in machine learning for where A is a positive semi-definite matrix. This is used a lot in many fields of science, such as machine learning. For example, PCA and many of the spectral dimensional reduction methods have these form. And this is actually also used in linear algebra. So because this is the optimization problem for eigenvalue problem, for eigenvalue decomposition. Also, you see this in theoretical physics. You see it in telecommunications too. So a lot. In this case, this says I want, what does it mean? I want X, the matrix X, to be an orthogonal matrix. So I want its columns to be orthonormal, perpendicular to each other, but their length, I want them to be 1, each column. I can see this is the definition of Stoffel manifold actually. So I can convert this classical optimization problem to a Riemannian optimization problem by saying that minimize trace of X transpose AX subject to X belongs to the manifold of Stoeffel, which is a Riemannian manifold. We have discussed this in the lecture of Riemannian optimization. Take a look at that. Another example is X being positive semi-definite or positive definite. Then it belongs to the, we can convert it to a Riemannian optimization problem by saying that X belongs to the symmetric positive definite manifolds or SPD manifolds, right? Another example is Grassmannian manifolds. So this is a Stoeffel manifold, Grassmannian manifold, SPD manifold. Grassmannian manifold is for projection matrix onto a subspace. So whenever we say X transpose A, which means that we want to project the columns of A onto the column space of X, or the space spanned by the columns of X, right? You can see this X as the linear projection matrix. It is closely related to the Grassmannian manifold. And it's used a lot in linear projection, has a lot of uses. In, for example, machine learning, you can see PCA as this, principal component analysis, and many, many other cases. Even regression, linear regression, can be seen as a linear projection. If you take a look at the formula for linear regression, I think it was, as far as I remember, X transpose X inverse X transpose Y, something like that. So you can see these, the whole thing. I might be wrong in some details, but it was similar to this form. Okay, Y is the matrix of the labels, and X is the matrix of the data. So you can see the whole thing as U transpose Y. So you can see the whole thing as a linear projection thing, right? Okay. Now that we have seen all of these things, you can see the KKT backbone. So I think now that you know the theory behind many of these optimization algorithms, you can see the nirvana moment or the enlightenment moment of optimization. And what is that? That the backbone of the most of the optimization algorithms is KKT conditions and Lagrangian. That's an interesting sentence. Why? Backbone of most of the optimization is KKT conditions and Lagrangian. This is the enlightenment moment of optimization. Let's take a look at that. So when we were dealing with an optimization problem, we take derivative, set it to 0. These, do you remember? We know that the derivative of Lagrangian with respect to primal variables and dual variables should vanish to 0, should be 0. Also, so you can see, because Lagrangian, you can see it as a soft penalty of the objective function. Also, in the first order optimality condition, you have this. So derivative of f at the primal variable should primal solution should vanish to 0. So it's related to KKT conditions. First order optimization, second order, all of them. You can see in the derivation of many of them. We use KKT conditions. We use Lagrangian. Take a look at whatever we have learned in this course. I remember that almost in all cases, we use the Lagrangian of the function. In derivation of interior point algorithm, which was constraint second order optimization, used in many toolboxes, we used Lagrangian and KKT conditions. I remember when we were deriving, the method of Lagrange multipliers also was based on KKT conditions. I remember in distributed algorithms, derivation of ADMM, it was based on KKT conditions and Lagrangian. Many of them, if you take a look at whatever we learned, go back and see, we are using Lagrangian on KKT conditions. So they have some shared knowledge between all of these optimization algorithms. And now take a look, sit back and take a look at all of the algorithms that you have learned and review them in your mind. You can see that they are all connected to each other. They're sharing ideas with each other. Even in many algorithms, do you remember For example, AGM. Take a look at AGM, accelerated gradient method. What was it doing? It had, I remember it had X and Y. So it introduced some additional variable. You saw that in many of the other algorithms. We also saw that in the alternating optimization. So because it was alternating between X and Y in AGM. So I'm saying that there are connections between algorithms. AGM is connected to alternating optimization. Also, I remember some other algorithms had this similar idea. Many of the algorithms were using the log of the history, similar to what we have in momentum. So they have shared ideas in that case. So if you take a look at them, they are using sharing ideas. Or coordinate descent. Maybe you can see it as an alternating optimization because you're alternating between the coordinates, right? So you can see different families of algorithms have some shared ideas, some have some connections with each other. So they have ideas shared between them. Okay, now acknowledgement. Some slides of this slide deck are inspired by Professor Stephen Boyd, the ellipsoid method and also the cut-in plane method. Boyd has some good lecture notes on those. You can take a look at them at Stanford University. Our tutorial also has some materials of this slide deck, tutorial 16. Okay, some references, let's review them in this slide deck. So Boyd and Vandenberg at Stanford, this is the lecture notes for cut-in plane methods. You can take a look at that. Also, this is a book, Numerical Analysis, because when I said, do you remember optimization algorithms? If we can't find a closed-form solution, we need to use numerical analysis. So you can take a look at that. Also, analytic centers. It was one of the algorithms for cut-in plane methods. Do you remember? For cut-in plane algorithms, family of methods, I mentioned some of the famous methods in that family of methods, such as these analytic centers. Another one, and again, analytic centers. These were proposed in 1993, 1995. Another one, analytic centers again, 1995. Ellipsoid method, 1980. Ellipsoid method in 2009. Cutoff method with space extension in convex programming problems. What was that? Let me take a look at that to remember. 8. Okay, 8 to 11. There are different papers which propose ellipsoid method. 8 to 11. Let's take a look at them. 8. So cutoff method with a space extension in convex programming problems proposed in 1977. Also these papers. So informational complexity and efficient methods for the solution of convex extremal problems in 1976. This is also ellipsoid method. So another one, evaluation of the informational complexity of mathematical programming problems in 1977. See, many of the authors are the same. Also Uding. So one of the authors who proposed ellipsoid method was Shor. Shor is a famous scientist in optimization. Another one is Uding et al. And also Nemirovsky. Udin and Nemirovsky. So this one is evaluation of the informational complexity of mathematical programming problems in 1977. The other one is optimization methods adapting to the significant dimension of the problem, 1977. All of these propose ellipsoid method. So this one in 1979, a polynomial algorithm in linear programming. What was it for? 12. Let's take a look at that. So 12 was when we used ellipsoid method in linear programming. Do you remember? Okay. So it is a famous paper, right, in Russian Academy of Sciences. Another lecture note by Boyd et al. An ellipsoid method. So this is a good lecture note of Stanford University by Boyd for the ellipsoid method. You can take a look at that. Also, this one, yes, this one is a book on Minimax and applications in 2013 by Du and Pardalos. So do you remember I said under some conditions, Minimax and maximin are equivalent. You can find those conditions in this book. Also, there is a paper on some thoughts on the Minimax principle in 1972. I think it discusses that it can be used in game theory as a good strategy, as far as I remember. Okay, this paper is also our tutorial paper on optimization. You can take a look at that. And I think it's a good tutorial. Okay, thank you very much. I hope this course has been useful for you.